This lecture covers the second part of Newton's unification process. In the first part of that process, we used the law of universal gravitation, Newtonian gravitation, to demonstrate Galileo's kinematics of a projectile. That is, all objects near the surface of the Earth fall with the same constant acceleration, regardless of their mass, in the absence of air resistance. Now, in the second part of the unification process, we use the exact same physical principle to now take a look at Kepler's laws of planetary motion. I have this presented to us as a problem. Let me go ahead and read the problem to you, copy it down in your notes. Unification Part 2. In a simplified form, use Newtonian gravitation to derive Kepler's third law. Assume that the planets orbit the sun in uniform circular motion for simplicity. Now recall Kepler's first law. All the planets orbit the sun in elliptical orbits, not in uniform circular motion. However, to demonstrate that using the law of universal gravitation, it requires two-dimensional calculus in polar coordinates. Of course, we're going to skip over those mathematical details and simplify the problem. When we do, we'll just simply assume that the planets orbit the sun in uniform circular motion. This then makes the problem algebraic. Okay, and then secondly, of course, we have Kepler's second law, which is that rather strange law, the law of equal areas. I will ultimately show you a version of Kepler's second law in the course of this derivation. We're going to derive Kepler's third law. But when I do, we are only going to do so in an algebraic way and in a simplified form. Later on, for those of you enrolled in AP Physics C, you will see a much more rigorous proof of Kepler's second law. Okay, let's go ahead and get to the third law. If you recall from the opening unit of this course, for those of you in Conceptual Physics AB, and Honors Physics AB, you saw Kepler's third law in the following way. You saw Kepler's third law, this. P squared is equal to A cubed, where P was the sidereal period of the planet measured in terms of years, and A was the semi-major axis of the elliptical orbit in terms of astronomical units, in terms of AU. Okay, recall that Kepler ultimately discovered this law empirically from Tycho's data. Also recall that Kepler spent the rest of his life looking for a reason for the three laws of planetary motion. He never did discover that reason. That's what the law of universal gravitation is now going to show. Okay, now we're going to change the notation here for Kepler's third law in this derivation. We're going to change the notation in the following way. Okay, let me draw a diagram here for simplicity first. So let's say right here is the orbit of the planet about the sun. Here's the sun. The sun has some mass. We'll refer to that as m sun. Okay, and then right here is the planet itself with a mass m. The radius of the circle here we simply refer to as r. That's then going to take the place of a in our expression. So we're going to write the right-hand side of the expression as r cubed. Okay, and then the left-hand side of the expression is just the orbital period of the planet. It's the sidereal period. When talking about uniform circular motion, we always refer to that as capital T. So then therefore, we're ultimately going to derive Kepler's third law as T squared equals R cubed using this notation here from what we've already seen for uniform circular motion. Okay, let me go ahead and do a little bit of erasing here. And now here's how this derivation begins. According to Newton, there's only one force exerted on the planet, and that's the force of gravity. That is, like so. And that force of gravity is then therefore going to give us a centripetal acceleration inwards towards the center of the circle where the sun lies. So now let's write F equals ma for this situation. We have then, first of all, the force of gravity, capital G, times the mass of the sun, times the mass of the planet, divided by distance squared. This then equals mass times acceleration, the mass of the planet multiplied by its centripetal acceleration of v squared over r. And now right off the bat, if I do a little bit of canceling here, here's kind of like a simplified version, if you will, of Kepler's second law, the law of equal areas. I'm going to go ahead and cancel out the mass of the planet, like so, and one of the distances r, like so. And then off to the side, let me now take what's left here and take the square root to ultimately describe the orbital speed of the planet. The orbital speed of the planet is then therefore this expression here. Okay, here's how this expression works, and this is once again a grossly simplified version of Kepler's second law. Notice that the closer the planet is to the sun, in other words, if r is small, the faster it moves in its orbit. That's ultimately describing the orbital speed of a planet. So the closer a planet is to the sun, the faster it moves. Now, if you go all the way back to Copernicus, remember that Copernicus made that assumption. He assumed that the closer the planet is to the sun, the faster it moves in its orbit. He didn't have a physical reason for that assumption, but it ultimately fits the appearances, of course, of what we see in the sky. We now have a reason for that by using the law of universal gravitation. Okay, let me go ahead and erase this. And now let's get back to this step here. What I'm going to do is, in this step, make a substitution for the speed v. Recall from uniform circular motion that the speed v is equal to the circumference of the orbital circle divided by the period. So let's go ahead and take this, plug it into here, and I have to square all of the terms when I do. So here on the left first, I have g times the mass of the sun over r. And this then equals v squared on the right-hand side of the expression, which is 4 pi squared r squared divided by t squared, like so. So take a look at that carefully. Once again, we take the speed v here, plug it into the expression, and square the terms. And now what I'm going to do is take this expression here, and I'm going to cross multiply and solve for t squared. Here's what I obtain when I do. So if I solve for t squared by cross multiplying, I get the following. This expression here. So take a look at this carefully. Take the r and multiply it by the r squared to obtain an r cubed, and then move the capital T squared up here to the left and the other terms over to the right. When you do, you end up with this expression here. Notice mathematically what this is saying. It's saying that T squared is proportional to r cubed. So this right here is starting to show us the mathematical form of Kepler's third law. However, we saw Kepler's third law as T squared equals r cubed. Therefore, if t is measured in terms of years, and r is measured in terms of astronomical in the units AU, what should this number here in the parentheses be? It should be 1. Let's see if it is. Now, the easiest way to see this process is to take this expression and move the r cubed down to the denominator here on the left. That is like so. And now what I'm going to do is I'm going to plug in the numbers here and then see what we get. Now, what are the numbers? First of all, of course, we have capital G. Capital G, as I mentioned earlier, is the following number, the universal gravitational constant in metric SI units. And then we also have in the expression the mass of the sun. What is the mass of the sun? Well, in order to know what the mass of the sun is, you need to know what another number is equal to. You need to know exactly what 1 AU is equal to. Measuring 1 AU is difficult to do. It was measured for the first time successfully in the 18th century when two rare celestial events occurred, one in 1761 and another in 1769. In those 2 years, there was a very rare, what is called transit of Venus. A transit of Venus is kind of like an eclipse. As seen from the Earth, the planet Venus passes across the face of the sun. This is actually a very rare event. It only occurs a couple of times per century. The last time that one occurred was a few years ago. Here, I was able to observe it in Los Angeles one afternoon. Suffice it to say, however, if you watch a transit from two different locations on the surface of the Earth at the exact same time, you could use some geometrical parallax to determine the distance from the Earth to the Sun, thereby measuring 1 AU. I described this in a little bit more detail in a short screencast that is also posted in today's folder. That screencast is presented to you as an Edpuzzle. Make sure that you watch that screencast. But if you can measure 1 AU, you can then ultimately determine, using the law of universal gravitation, what the mass of the sun is equal to. Now, 1 AU is quite large. It's 93 million miles. It's 150 million kilometers. This was first measured successfully in 1761 and in 1769 during the transits of Venus. it is equal to 1.5 times 10 to the 11th meters. That's 150 million kilometers. That's what 1 AU is. So that's how we know the distance from the Earth to the Sun. It was first measured in the 18th century during 2 transits of Venus. Once we know this number, we can then determine the mass of the Sun using the law of universal gravitation. The mass of the Sun is 2 times 10 to the 30th kilograms. Okay, so now what I'm going to do is I'm going to take this number here, the mass of the Sun, plug it into here, and also plug in capital G. And then let's calculate this ratio. Let me put it right here like so. Okay, so now I have, first of all, 4 pi squared, so 4 times pi squared, and then divided by parentheses, capital G, punching that in, multiplied by the mass of the Sun. And now when I punch in all of these numbers, I get something that is nowhere near 1. Instead, I end up with about 2.96 or so times 10 to the minus 19. But what are the units of this quantity? Well, this quantity here is all in terms of metric SI units, and it's measuring a time squared divided by a distance cubed. Therefore, it is seconds squared per meter cubed for that reason. I'm in metric SI units. So I'm in the wrong units. What I have to do is I have to convert the seconds into years, and I have to convert the meters into AU. Let's see what happens now when I do. Okay, now I have one of the conversion factors that I need. It's written right here on the board. 1 AU is 1.5 times 10 to the 11th meters. So let's begin to multiply. I'm going to multiply by now quantity. 1.5 times 10 to the 11th meters cubed per 1 AU, cubed like so. Notice that the meters cubed will cancel here and here, like so. But then I also have to convert seconds, here it is, I have to convert seconds into years. Remember that I've previously mentioned the conversion factor between seconds and years. It's an easy number to remember. It's about pi times 10 to the 7th. That's 31.5 million seconds in a year. 60 seconds per minute, multiplied by 60 minutes per hour, multiplied by 24 hours per day, multiplied by 365 days per year. If you multiply those numbers together, you get about 31.5 million. Pi times 10 to the 7th, about 3.15 times 10 to the 7th seconds. So 1 year is equal to 3.15 times 10 to the 7th seconds. Let's now go ahead and plug that in. So now what I multiply is the following. 1 year quantity squared over 3.15 times 10 to the 7th seconds quantity squared. Like so. Notice once again how the units here are going to work. Seconds squared cancels out with seconds squared. Like so. And then the units that I'll be left with are years squared per AU cubed. So now let's see what happens when I punch everything out. All right, so the number that I'm going to obtain, I'm going to put right here in this space. And then once again, when I do the math here in just a moment, we will now be in the correct units. Years squared per AU cubed. All right, now I still have this number here in my calculator. So then multiply by 1.5 times 10 to the 11th raised to the 3rd power. And then divide that by 3.15 times 10 to the 7th squared. And then even though I've been rounding some numbers off a little bit here as I've been proceeding through this calculation, out several decimal spaces, the number is in fact equal to 1. T squared is equal to r cubed as long as t is measured in terms of years and r is measured in terms of astronomical units. So what we've done here in, yes, admittedly, a simplified form is we've used the exact same physical principle that I did earlier to explain Galileo's kinematics of a projectile, now to derive Kepler's laws of planetary motion. In completing this calculation, Newton unifies together motion near the surface of the Earth and motion in the heavens as the same thing. In other words, the law of universal gravitation. As impressive as this problem is and the first part of the unification process, Newton still, however, has to prove his theory with a specific numerical example. He does so, and he presents that proof in his original text of Principia. It's probably the most important physics problem that has ever been done in history. I will do that problem in the next lecture.